Okay, so in the previous video, we defined what it means for a transformation to be one-to-one and onto. So let's take a look at some examples of linear transformations and see how we can identify whether the transformation satisfies one or both of these properties. And let's use our kind of matrix approach to help us with this. So if we want to kind of think about what this matrix might look like, T of E1, that's just the vector 1, 0, 0. That vector is going to get mapped to 1, 0, since it has x1 equal to 1 and x2 equal to 0. T of E2, that's going to get mapped to the vector 0, 1. T of E3, that's going to get mapped to the 0 vector. So this has a matrix representation where the first column would be 1, 0, the second column would be 0, 1, and the third column would be 0, 0. We don't need the matrix necessarily to identify these properties. For example, I can see from this fact over here that this transformation is not one-to-one, since we have more than one vector which is being mapped to the 0 vector. So the image of the 0 vector would be the 0 vector, and now we can see that there are other vectors, here's one such one, that also get mapped to the 0 vector. So this mapping over here, keep in mind, is a projection. We're mapping from R3, where we have x1, x2, and x3, and we're projecting these points into the x1, x2 plane. So any point under this map is getting mapped down here. So this is why this function is not one-to-one, but we can map to any point that we want in R2. So this would be onto, but it's not one-to-one. So we have a yes for onto, and we have a no for one-to-one. Let's take a look at the next map, and we'll think about this similarly, that if we want to think about, well, what does the matrix of this transformation look like? Well, T of E1, right, that's the vector that has x1 equal to 1, x2 and x3 equal to 0. So its image would be 0, 0, minus 1. The image of E2 would be minus 1, 0, 0. And the image of E3, that would be 0, minus 1, 0. So this matrix representation for this transformation, the first column would be the image of E1, the second column is the image of E2, and the third column is the image of E3. And here, you hopefully can look at this map and convince yourself that because the mapping depends on x1, x2, and x3, that there are no two vectors, any two different vectors in the domain are going to get mapped to different vectors in the codomain. So there's no issue about multiple vectors being mapped to the same thing. So this map is indeed one-to-one. And each individual vector in R3 in the codomain over here, we can find some pre-image that gets mapped to it. So if you want to plug in any vector over here, you can find values for x1, x2, and x3 so that the vector over here, x1, x2, x3, has an image in the codomain. So this is also onto. And this matrix A that we have, if we were to do some row operations on it, hopefully it's pretty quick to verify that its equivalent reduced row echelon form matrix is the what we would call the identity matrix here. So it's a matrix that has ones on the diagonal and zeros everywhere else. So here there's something nice about the reduced row echelon form of the transformation matrix and how it relates to its properties of being one-to-one and onto. Example 3, we're now mapping from R2 up to R3. And this map is defined by we're taking x1, x2, and we're mapping it to the vector x2, 0, x1. And for this mapping, we can determine right away that this is not onto, since we're only mapping to vectors in R3 that have 0 in the x2 position. So we're not going to be able to find anything whose image under this map has a non-zero entry for the second entry. So this is not onto. The next question is it one-to-one? And this is one-to-one, since any vector that has unique x1 and x2 coordinates is going to get mapped to a different vector under this map. But we can also write this out as a matrix. We have standard vector 1 in R2. It would wind up getting mapped to 0, 0, 1. The second standard column vector, that's going to get mapped to 1, 0, 0. So the matrix representation here would have its first column of 0, 0, 1, its second column of 1, 0, 0, and that would be that. So what we can see is that it's possible to be both one-to-one and onto. It's possible to be onto but not one-to-one, like this first example. And it's possible to be one-to-one but not onto, as in this last example. So when we're going from a two-dimensional space to a higher three-dimensional space, right, we're not going to be able to find a surjective in onto map to do that. And when we're mapping from a higher dimensional space R3 down to a lower dimensional space R2, there's no way that we can do this in a way that we're going to get a one-to-one map. Since we have more things over here being mapped to less things over here, we're going to have multiple vectors in R3 that are mapped to the same image in R2. But let's take a look at some of the properties of these matrix representations that we had. So notice that for the functions or the transformations that were one-to-one, so that was the second example and the third example that we looked at, that these matrices, at least when we put them in reduced row echelon form, right, they have a pivot in every column. Whereas this case the first case we looked at, which was not one-to-one, right, it had a column that was missing a pivot. So let's just kind of write that observation down, and that is if the reduced row echelon form of matrix A has a pivot in every column, then it's going to be one-to-one. And if we similarly look at properties of this matrix that might indicate whether or not the map is onto, well, we had our first example was onto, and the second example was onto. And notice that what these matrices have in common is every row of the matrix in its reduced row echelon form, every row has a pivot. This third example, it was not onto, and notice the matrix representation of this transformation had a row that didn't have a pivot in it. So identifying properties of a transformation, a linear transformation being one-to-one or onto, it may be very useful for us to write out these transformations in their matrix form and then look at properties of the matrix, namely pivots, and think about how does that relate to whether this is going to be a one-to-one or an onto function. So we will generalize this discussion on the next slide.